So we're supposed to find the first four non-zero terms. What you want to do is find a Maclaurin series for this and then integrate it term by term. And to make things a little easier, you should consider a Maclaurin series for like the simplest version. How about 1 plus x? Natural log 1 plus x. Because if we can come up with a Maclaurin series for this expression, then we can easily find out the Maclaurin series for this one. Just plug in 5x to the fourth in for x everywhere where you see in the Maclaurin series. So remember, the formula for the Maclaurin series is that it is the function kept the same, and you plug in 0 into it. Wait a second. No, that's not. This isn't going to work because natural log of 1 is 0. Oh, I gotta think. I gotta pause the video. No, I think we're gonna have to stick with this. I don't think there's any way around it. We need that 1, or else we won't be able to have the substitution necessary. So let's go through the process of Maclaurin series. It's a sum from n equals 0 to infinity of the nth derivative, and it's Maclaurin, so it's at 0, n factorial times x to the nth power. So the first term, if I plug in 0 into the no derivative, natural log of 1 is 0, so the first term is going to be 0. But the second term, the derivative, is going to be 1 over x plus 1. Or in other words, to help us with derivatives, let's make that its equivalent form of 1 plus x to the negative first. So that's the derivative. If I plug in 0 into the derivative, I get out 1, and then 1 factorial is 1, and then it's x to the first. And so the second derivative, I'll stuff it over here. Second derivative, the negative 1 comes down. Now it's the negative second, and then the chain rule just means times 1, so we're all set there. So it's plus, if I plug in 0 into the second derivative, I get out 1. 1 to the negative second is 1, so that's a negative 1 over 2 factorial, x to the second. And then the third derivative, the negative 2 comes down, multiplies, then it gets reduced by 1. So the third derivative, I plug in 0, I get out 2, and then it's 3 factorial, which is 6. And then I need the first 4 non-zero terms, so I need one more derivative. The fourth derivative is going to be negative 6, 1 plus x to the negative fourth. If I plug in 0 in there, I get out negative 6 in the numerator. So that's what this evaluates to be at the fourth derivative when we plug in 0. And then that's the fourth derivative, so 4 times 3 times 2 times 1. The denominator is, 24. That's x to the fourth. Okay, cleaning that up a bit, that's x subtracted by 1/2 x squared plus 1/3 x to the third subtracted by 1/4 x to the fourth. And so that's for g of x. We wanted f of x. That's just going to be substituting 5x to the fourth everywhere where we see an x, because our original expression was 1 plus x. If you plug this in for x, it's the same thing as plugging this in for every x you see down here. So the terms are 5x to the fourth subtracted by 1/2. Now 5 squared is 25, and then that's x squared. X to the fourth squared, so that's going to be x to the eighth. And then here that's 1/3 times 5 to the third, so that's 125. And then that's x to the fourth raised to the third power, so that's going to be x to the 12th. And subtracted by 1/4. 5 to the fourth power, 625. That's x to the 16th, I think. Yeah, 4 times 4 makes 16. So there, we've got f of x. Now we just need to find capital F of x by integrating each term. So antiderivative here, there's going to be a 1/5 that comes out. That makes x to the 5th. You can check that. And then here, that's a 9 that comes out. So that's 25 over 18 x to the 9th, and then a 13 that comes out, so that's a 39 in the denominator. It's 125 x to the 13th, and then a 17 that comes out, so whatever 17 times 4 is for the denominator, that's 68 in the denominator. That's 625 x to the 17th. Simplify the fractions if you can. I don't know off the top of my head if those can simplify, but that's it. That's the first 4 terms.